All right, we're starting chapter 5. Test is chapters 3, 4, and 5. 5 is starting to put together everything that we've talked about so far, both the descriptive statistics and probability. We learned the descriptive statistics, measures of center, measures of variation, and z-scores in chapter 2 and 3, and then talked about probability in chapter 4. So in chapter 5, we're going to start talking about using those descriptive statistics to predict what may happen in the population. All right. In the event or experiment of rolling a die, let's say rolling a die 60 times, because I added up those frequencies and got 60. This is a frequency distribution that we talked about in chapter 2, I think. If you want to find the mean of a frequency distribution, remember what this means. 8 times the die landed on 1, 10 times it landed on 2, and so on and so on. To find the mean of the frequency distribution, you multiply each number times its frequency, and then add all of those up and divide by the total frequency. If you do that, you find that the mean of this rolling a die 60 times is 3.6. Now that is an experiment, so that's a sample mean is 3.6 and the standard deviation is 1.7. We could do that in chapter 2, no problem. In chapter 4, we learned that the probability of a 1 is 1/6, the probability of a 2 is 1/6, and all the way up to the probability of a 6 is 1/6. In chapter 5, we're going to figure out how to construct what's called a probability distribution rather than a frequency distribution. Frequency distribution describes what did happen in an experiment, what we observed. A probability distribution will tell us what we can expect to happen. And when we talk about this in just a minute, this probability distribution and how to find its mean, the mean of the probability distribution is darn close to what we observed when we actually rolled the die 60 times and found the mean of the frequency distribution. So it sounds like probability distributions can be used as good predictors of what would actually happen if we conducted the experiment. All right, section 5.2 introduces the important concept of a probability distribution, which gives the probability for each value of a variable that's determined by chance. We will give consideration to distinguishing between two outcomes that are likely to occur by chance and outcomes that are not likely to occur by chance, which means they're unusual. All right, here are the terms that you need to have on your study guide for chapter 5. Number 1, a random variable. A random variable is a variable, typically represented by X, that has a single numerical value determined by chance for each outcome of a procedure. If the procedure is rolling a die, then X can stand for the number of dots facing up when that die stops rolling. The possible values for X would be a 1, a 2, a 3, a 4, a 5, or a 6. But the random variable is X, and it has a single numerical value determined by chance. A probability distribution gives the probability for each value of a random variable. Think about the frequency table for that rolling a die 6 times, and then the probability distribution just said the probability that it lands on 1 is 1/6, the probability that it lands on 2 is 1/6, all the way until you've given all the possible values for the probability distribution. You need to understand the difference between continuous random variables and discrete random variables. And we've already used that word continuous and discrete. Continuous random variables have infinitely many values, and those values can be associated with measurements or a continuous scale without gaps or interruptions. If you're talking about weight, that is a continuous measurement because it can be measured to an infinite amount of precision if you have an infinitely precise scale. All right, somebody actually can be measured to weigh 180.7492 and on and on and on if you had an infinitely precise scale. A discrete random variable is either a finite number of values or a countable number of values, where countable refers to the fact that there might be infinitely many values, but they result from a counting process. The best example that I can think of to help you keep continuous and discrete straight in your head, the number of eggs that a chicken lays, that's discrete. It's either 1 egg or 2 eggs or 3 eggs. It's never going to be 1.4782 blah, blah, blah x. The number of ounces of milk that a cow gives is continuous because it could be measured to an infinitely precise level if you had an infinitely precise scale. So let's practice identifying these as continuous or discrete. The total amount in ounces of soft drinks that you consumed in the past year. Would that be a continuous variable or a discrete variable? Continuous because it could be measured to an infinite precision level. If you had an infinitely precise scale, you could actually drink 64.297 and go on and on and on with the number of ounces that you drink in a year. The number of cans of soft drinks that you consume in a past year. I think this would be better worded if it said the number of cans of soft drinks that you opened in a year. All right, because the argument can be made, you don't have to drink a whole can of soda just because you opened it. And then we get into, well, did you drink 1/10 or did you drink 1/100th? If you don't want to go there, just think of the number of cans that you opened. Would that be continuous or discrete? Yeah, that's discrete. What about the number of movies currently playing in U.S. theaters? Discrete. That's either 100 or 1,000 or 10,000, but it's not 10,000 point something, something, something. The running time of a randomly selected movie. That's continuous. That could be measured to an infinite degree of precision. You'd be 10th of a second, 100th of a second, 1,000th of a second, but there's no finite number of choices for the running time of a movie. And the cost of making a randomly selected movie. Is there some point beyond which we cannot be more precise when you're talking about cost of something? We have a debate. Pennies are as precise as we can be. So, I either have $3.25 or I have $3.26. I can't have $3.25 point something something that goes on forever cents. So measurements of height or weight or time, those are continuous. But when we're talking about something that has a finite level of precision, like money, that's discrete. Requirements for a probability distribution, all of the probabilities have to add up to 1. If you made a probability distribution for rolling a die, in the left-hand column you would have the possible outcomes when you roll a die, just the numbers 1 through 6. And in the right-hand column, you'd have the probability that the die lands on each number. All of those probabilities have to add up to 1. 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 has to add up to 1. And the probability has to be between 0 and 1 for every value of x. Well, that's just restating the definition of probability. Probability is always a number between 0 and 1. So each probability has to be a number between 0 and 1, and all the probabilities have to add up to 1. Here are some formulas just to make you appreciate your calculator, because we're not really going to use those formulas. We're going to figure out how to put a probability distribution into the calculator and let it find the mean, the variance, and the standard deviation for the population. All right. Finding the mean and standard deviation of a probability distribution using the TI-83 and the 84. Groups of 5 babies are randomly selected. In each group, the random variable X is the number of babies with green eyes. If there are 5 babies being checked, surveyed, what are the possible answers to the question, how many of them have green eyes? There could be 1 baby with green eyes or 5. So I'm making this harder than it is. There could be no babies with green eyes, 1 baby with green eyes, 2 babies with green eyes, all the way up to 5 babies with green eyes. This left-hand column has to be all the possible outcomes for the procedure, whatever it is. And then I don't know where these probabilities came from. It has something to do with the likelihood the likelihood of babies having green eyes. But it looks like there's about a 53% chance that out of 5 babies, none of them would have green eyes. And there's about a 36% chance that only 1 of them would have green eyes, and so on and so on. Whenever you see 0 with a plus, it's not impossible that all 5 babies would have green eyes, but green eyes aren't that common in babies. It's highly, highly unlikely. If you just put 0 here, you would be saying it's impossible. 0 with that plus means it's almost 0, maybe 0.00000001, but it's not very likely to happen. Not impossible, just highly unlikely. When you enter this probability distribution on the calculator, you can enter that 0 plus as just 0, and it won't mess up your distribution. All right. Is it a probability distribution? Are all of these probabilities between 0 and 1? Yeah, they are. Do they all add up to 1? Well, you could punch it all on the calculator to double check, but yes, they all add up to 1, so it is a probability distribution. We want to use the calculator to find the mean and the standard deviation of the probability distribution. So right here in red is exactly what to punch on your calculator to get the mean and the standard deviation of that probability distribution. You put both of these columns in as lists on your calculator. Go to Stat Editor and type in the values of X as list 1 and the probabilities as list 2. Let's see. Stat, and then number 1 for edit. You remember how to clear a list you already have in? Just move the cursor up to the list name and hit clear and enter so that you start with a clear list. The possible values for number of babies with green eyes would be 0, 1, 2, 3, 4, 5. Those are the only possible answers to the question, how many of these 5 babies have green eyes? And then in list 2, put those probabilities. Probability of 0 green eyes is 0.528. Probability of one baby having green eyes is 0.36. Probability that two babies will have green eyes is 0.098. Probability that three of the babies will have green eyes, 0.013. Probability that four of the babies will have green eyes is 0.001, which is highly unlikely. The probability that all five will have green eyes is not really zero. That's what the 0 plus indicates, but so darn close to zero that you can call it zero without messing up the statistics. So just leave probability of all five as being zero. Hey, just looking at those values, which numbers of babies having green eyes would be considered unusual? Remember what we use as the cutoff probability for what's unusual and what's not? I don't understand yet. Did you say 1 and 0? I'm not sure where I'll think about it, but I can't think of where those numbers are coming from either. What's the number of standard deviations within which we consider data to be usual? All right, within 2 standard deviations. What z-scores indicate data to be usual? Anything between -2, which is 2 standard deviations below the mean, and +2, which is 2 standard deviations above the mean. What percent of the population lies within 2 standard deviations of the mean for normally distributed data? 95% lie between the z-scores -2 and +2. So what percent lie outside those z-scores? 5%, which corresponds to a probability as a decimal as what? 5% as a decimal. 0.05. 0.05 is the cutoff in probability for what we call usual or unusual. If something has a probability less than 0.05, we say it's unusual. So how many out of 5 babies, how many would be unusual to have that many babies with green eyes? Probability of 3 of them having green eyes is less than or just a little over 1%. 4, probability is way less than 5%. 5, very, very low probability of that happening. Probability of 2 is greater than 0.05, but any more than 2 of those babies having green eyes would be considered unusual. It would be unusual to find a group of 5 babies where 3 or 4 or 5 of them had green eyes. All right. Does everybody have list 1 and list 2? All right. Quit the stat editor, just second and quit. Then press, and right here is where I'm looking, stat. Move the cursor 1 to the right and choose number 1 for one variable stats. Stat, move the cursor to calc, and then number 1, one variable stats. Press enter. And then tell the calculator which list you want it to use for your one variable statistics. You want to use list 1 and list 2. So in parentheses, where does it say that? Type the names of your 2 lists separated by a comma. Open parentheses, list 1 is in blue over the number 1. Comma is right above the 7. And list 2 is right above the number 2. You're telling the calculator, I want you to run one variable statistics using list 1 and list 2. enter, and there's our information. What does X bar stand for? The symbol X bar? Are you getting something different? Okay, let me see your stat editor. Go to stat, and you might have to just hit enter to get out of that. Go to stat, and number 1, let me see your 2 lists. 0, 1, 2, 3, 4, 5, 0.528, 0.36, blah, 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 blah. Okay, that doesn't seem to be the problem. Then go to, yes, stat and calc, and number 1, and open parentheses. Gosh, I don't see what's wrong. Type list 1 comma list 2 for me again, and let's see. Yeah, above this. Oh, okay. I meant the button above the 7. Now try list 2. Is anyone getting these numbers?
The first list and the second list.
Separated by a comma. Okay, let's see. Clear that. And oh, you didn't have one bare stats up first. Look right here, press stat and move the cursor over 1. No, not second stat, just stat. Stat, move the cursor over to calc, enter number 1, and then say list 1 comma list 2. You didn't tell the calculator what you wanted it to do with list 1 and list 2. Any other questions about getting this screen? All right. Tell me what the symbol X bar stands for. That makes me nervous. It's important that you know what these symbols stand for. That's why when I created the 3.2 study guide template for you, I put symbols on that study guide. The rest of the semester, I'm going to be flashing up on the screen sigma equals blah, blah, blah. If you don't have in your head sigma equals population mean, then you're not going to know what I'm talking about. Can you tell me what X bar is, or what? Which mean? No, mu is the population mean, X bar is the sample mean. So if you realize you don't understand what these symbols stand for, if you don't have words associated with each of the symbols, that's something you need to be working on and something you need to have in your study guide. The calculator will interpret your list as a frequency table and will display X bar rather than mu. See, let me go back to stat edit for a second. You don't leave this screen, but let me show you something. Stat and edit. My calculator thinks that 0 happened 0.5 times, and 1 happened 0.36 times, and 2 happened 0.098 times. That's what my calculator thinks that I've entered. And I don't care what it thinks as long as it gives me the right answer. But it's giving me X bar because it thinks, oh, she's asking for the mean of the sample. Actually, only I know that this is a probability distribution. And so what it gives me for X bar is actually the mean of the probability distribution. It's the answer to this question. What's its mean? Its mean is 0.599. And its standard deviation is sigma, 0.725. Sigma with the X beside it is the standard deviation of the probability distribution. This arrow pointing down equals 1 is telling me that, yes, all of my probabilities add up to 1. Everything you need is already typed for you. Just read it. All right. Any questions about number 10? Answering these three questions right here. The mean, 0.599, standard deviation, 0.725. All right. Here are rounding rules. Round results by carrying one more decimal place than the number of decimal places used in the original data. That's what we said for mean and standard deviation before. So if our original data is to the nearest whole number, we'll give the mean and the standard deviation to the nearest tenth. But you don't have to memorize that because the homework will tell you. All right, according to the range rule of thumb, most values should lie within 2 standard deviations of the mean, or have z-scores between -2 and +2. We therefore identify unusual values by determining if they lie outside these limits. If you want the maximum usual value, and remember you can substitute in your own head, you can substitute the word shocking for usual. The maximum number that would not shock me would be the mean plus 2 standard deviations. The smallest number that would not be considered shocking is the mean minus 2 standard deviations. Using probabilities to determine when results are unusual. Something is considered to be unusually high if the probability of that number or more is less than 0.05. Now, let me give you an example of this for it to make sense. If you flipped a coin 100 times and then made a probability distribution for that, if you got 0 heads, that would be unusual. Or just 1 head would be unusual. How many heads would you expect to get out of 100 tosses? 50. All right, you'd expect the coin to land on heads 5 times. But you really wouldn't be, or I didn't mean 5, I meant 50. But you really wouldn't be shocked if it was 40 probably, or wouldn't really be shocked if it was 60. But there's some point out there, I'm not sure exactly where that point is, but definitely to get only 10 heads would be unusual. That would be let me back up. Maybe 90 heads would be an unusual high number of heads because the probability of getting 90 or 91 or 92 all the way up to 100, you could add all those probabilities up and it would still be less than 0.05 if you were using a fair coin. So an unusually high probability means the probability of getting that or more is less than 0.05, and an unusually low number of successes is the probability, excess successes among N trials is unusually low if the number of successes of, that's supposed to be of instead of if, the probability of X or fewer is less than 0.05. Flipping a coin 100 times and it only landing on 5 times, that's an unusually, wait, did I say a coin lands on 5? I didn't mean that. Flipping a coin 100 times and it only landing on heads 5 times would be unusually low because the probability of only 5 or 4 or 3 or 2 or 1, you can add up all of those probabilities and it's still less than 0.05. Tonight in the homework, I know what questions are going to be coming to my living room tonight. It's about the unusually high and unusually low. First thing I'm going to say to you is look back at slide, whatever that is. Unusually high, something's unusually high if the probability of that or more is less than 0.5, and unusually low if that or less is less than 0.05. All right. Finally, we get to do an example to see if it makes all of this make sense. The pea hybridization experiment. Probably by, who's the father of genetics? Somebody in biology. Who did the pea hybridization experiments? Gregor Mendel. The accompanying table describes the results from 8 offspring peas. The random variable X represents the number of offspring peas with green pods. So, Gregor Mendel was raising peas in the garden of the monastery, going out and picking a cluster of 8 of them, and then counting how many of the 8 peas had green pods. He had hybridized 2 different species is not the right word, 2 different varieties of peas. How many of those 8 have green pods? Well, the possibilities out of 8, there could be none with green pods, or 1 with green pods, or 2 with green pods, all the way up to 8 with green pods. That's the only possible answers to how many of these 8 have green pods. Find the mean and the standard deviation for the number of peas with green pods. That means just type this in as list 1, this in as list 2, and find the mean and the standard deviation. You can enter those 0 pluses as just zeros as long as you understand it's not actually 0, it's just very, very, very close to 0. If Gregor Mendel wakes up in the morning, goes out in the monastery garden, picks 8 peas, what is the most likely number of those peas that will have green pods? There's about a 31% chance that 6 of them will have green pods. So green pods must be the norm. All right? It must be, what he was expecting. The probability that there would be, how many would be considered an unusually low number of green pods? Yeah, because I don't think I said it exactly like I wanted to. How many numbers of green pods would be considered unusual? What number of, well, there's about a 10% chance that all 8 would have green pods. Which numbers have a probability of less than 0.05? 0 green pods would be shocking. Only 1 would be shocking. 2, 3 would be surprising. It's not until you get up to 4 till you get a number of green pods that would be considered usual, because there's greater than a 5% chance that out of 5 peas, 4 of them would have green pods. Not 5 peas. Out of 8 peas, 4 of them would have green pods. That's just making sure that you understand how to read and how to look at the probability distribution. Now let's find the mean and the standard deviation. Remember, that's under Stat and Calc. One variable stats for list 1, comma, list 2. You have to exit Stat Editor first. Exit your Stat Editor, and then tell the calculator you want one variable statistics for list 1 and list 2. I thought so, but maybe not. If it gives you, well, here's the answer. So if you have the same thing, then apparently you don't have to have the parentheses. For some reason, I just thought you did. What is the mean number of green peas? 6. That's what you should expect most often to happen, and that's exactly what you told me. 6 green pods is the most common result. So the mean is the mean is 6. And what's the standard deviation? 1.2. And you rounded that to the nearest tenth because the number of peas with green pods was to the nearest whole number. Use the range rule of thumb to identify a range of values containing the usual number of peas with green pods. Well, we have a minimum number that we would consider usual and a maximum number that we would consider usual. The minimum how do you get the minimum usual number of green pods? The mean minus 2 standard deviations is 6 minus 2 times 1.2, or 6 minus 2.4 is 3.6. So if I had 3.6 green or peas with green pods, that wouldn't be shocking. What is the maximum number? That would be considered usual. That's the mean plus 2 standard deviations, or 6 plus 2 times 1.2, and that is 8.4. If you picked 8 peas and 8.4 of them had green pods, would you be shocked? If you picked 8 and 8.5 of them had green pods, you would be shocked because that's not possible. You can't pick 8 and have 8.5 green pods. So when I list this range, let's see, range of values containing the usual number of peas with green pods, I'm going to list that answer as between 3.6 and 8 green pods. I'm not going to put 8.4 green pods because that's not possible. Debbie, what's making you frown? 3.6 is in the range of 0 to 8. 8.4's outside the, possible answers. Because you can't get 8.4 out of 8. It's just not possible. All right. Number 16, referring to that same table. Find the probability of getting exactly 3 peas with green pods. Well, you can read that straight off the table. The table gives us the probability of exactly 3 peas with green pods. It's 0.023. That's what the probability distribution is giving us. Find the probability of getting, can I make that go away? Find the probability of getting 3 or fewer peas with green pods. What does 3 or fewer mean? Yeah, 0 or 1 or 2 or 3. That's what 3 or fewer means. So just add up these 4 probabilities. 0 plus 0 plus 0.004 plus 0.023 is 0.027. The probability of getting 3 or fewer peas with green pods is 0.027. Which of these 2 probabilities do you look at to answer the question, is 3 an unusually low number of green pods? Is it answer A or answer B that you would use to answer this question? Here's where I'm going to type, look back at the definition of unusually low. The definition of unusually low, X is unusually low if the probability of X or fewer is less than 0.05. So 3 is an unusually low number of peas with green pods out of 8 if the probability of 3 or fewer is less than 0.05. So to answer the question, is 3 an unusually low number, would you use the probability for exactly 3 peas or 3 or fewer peas? 3 or fewer. That's what the definition of unusually low is. So the 0.027 is the number that you would compare to 0.05. Is 3 an unusually low number of peas with green pods? Yes, because why? Because because 3 out of 8, or 3, I messed that up, because the probability of 3 or fewer is less than 0.05. You have a problem exactly like this in the homework. Look back at this example if you need to remember how to determine if something's unusually low. Unusually high would mean the probability of that or more is less than 0.05. No, the probability, let's say 7 would be unusually high if the probability of 7 or 8 is less than 0.05. 0.05 stays the constant. That's the magic cutoff between what's usual and unusual. So if the probability of 7 or more was less than 0.05, then you'd say 7 is unusually high.
So if this was 0.072, that would be
That would not be unusual if you said 0.07. 0.07 is greater than 0.05, so that would indicate not unusual. All right. I have 2 more examples. I think we'll have time for them. Expected value. The expected value, goes on your study guide, of a discrete random variable is denoted by E. So E is what you expect to get, and it represents the mean value of the outcomes. E, oh, I can't write on that. E is the mean. In your notes on your slide, put E is the mean. Maybe this is an insurance policy, what you expect to gain or lose on your insurance policy. Or maybe it's what you expect to win or lose in Las Vegas. All right, it's the expected value, and it's just the mean of the probability distribution. Now, what are we going to do with that? The next slide has something straight off of television. The game show Deal or No Deal. Have you ever watched it? You know how it works? 25 gorgeous supermodels standing on risers, each holding a suitcase. The contestant comes out and chooses one suitcase to be her own or his own. And then the rest of the show, she's really betting whether or not she has the most money you can win. The most money you can win is $1 million. If right off the bat she picked the suitcase that had $1 million in it, then that's the most she could possibly win. She calls out numbers corresponding to briefcases, and each time she calls out a briefcase, the model opens the briefcase and shows the monetary value of what's inside the briefcase. The briefcases hold amounts between 1 penny and $1 million. And at the end, you want to be holding the $1 million suitcase. If a player, let's see, let me do one more bit of explaining just in case you haven't seen Deal or No Deal. Each time she calls out a number, the supermodel opens the briefcase, and that monetary value is now out of play. A very lucky person would pick the 1 penny, the $1, the $5, and get all of those briefcases out of play because those aren't the amount of money that you want to win. You try not to open the suitcases with big money because that's what you want to have left at the end. So if a player adopts the strategy of choosing the option of no deal, in other words, keep going until only one suitcase remains, the payoff is one of those amounts, and they're all equally likely. Find the expected value for this strategy. Now, for those of you who have watched the show, you know that when the contestant has eliminated, say, 10 of the suitcases or briefcases, a person called the banker will offer her an amount of money to quit playing. Stop now and I'll give you $500,000, or stop now and I'll give you, $200,000. The banker's trying to get her to quit before she wins the $1 million. So if she's determined not to quit, if she's going to keep going until there's only one suitcase, no matter what the banker says, how much can she expect to walk away with? Well, really, we can make a probability distribution. These are the possible outcomes from 1 penny all the way to $1 million. We're going to put that in list 1. And then I think there are 26 suitcases in all. Debbie, I just saw you counting them. Is that what you got? 26? Yeah. The probability that the one she's holding is the $1 million is 1 out of 26. So we're going to enter all the probabilities as 1 out of 26. And make sure that, well, let me go ahead and clear both lists. Make sure that you put the penny in as $0.01. The rest of the amounts are in dollars, so the penny has to be written in dollars. So if the last case she's holding, or the last model's holding is a penny, then she'll win 0.01. And I'm just going to stop talking and enter these other amounts. I can't get it where I can see everything I want to see at once. Oh no, I think I might have skipped a suitcase. Ah, crap. $1 million. Might have skipped 2 suitcases because I should have 26. Miss Abby, would you read the amounts to me? And I can't get both of them. Oh, wait, where did I get? Why do I have 4? What the heck? That's supposed to be 400. Let me get back to the top of my list. Read the amounts to me after a penny. Yep. Yep. Uh-huh. Yeah. Okay. Ooh, I don't have 75,000. 50,000 and then 75,000. Okay, it really doesn't matter what order these are in. So let me put in my 75,000. And then after 75,000, there's 100,000 and then keep going. What's after 100,000? All right, I left off the 400,000. I just couldn't get all the numbers and my calculator on the screen at the same time. 400,000. All right, so I have 26 suitcases in there. I'm going to go to the top of the next list, and the probability of any one of the suitcases holding the $1 million is 1 out of 26. You can enter that as 1 divided by 26. And the calculator will change it to a decimal. Now I have to do, I don't know how to copy. I think I have to do that 26 times. Now list the 26 possible outcomes and then the probability of each outcome. I think this is giving me carpal tunnel syndrome. All right, I have the same probability for all the outcomes. Now, what do I do when the homework or test question says, find the expected value? Because what do I know that that's the same thing as? That's the same thing as the mean. So just stat, first quit stat editor, then stat, calc, one variable stats, using list 1, comma, list 2. If the contestant was just going to turn down the banker and keep going no matter what the banker offered her, what would be the expected winnings? Say to the nearest dollar. Yep, 131,478. That's not a bad haul. I wouldn't mind winning 131,000 instead of $1 million. What's the value of the standard deviation? to the nearest dollar. $253,584. Ooh, that might just give me a different take on that strategy. The expected value, or if I wasn't in a statistics class, I'd probably say the average winnings would be about 131,000-ish. But look at the standard deviation. One standard deviation below the norm, below the mean, what are you going to win? You're going to be paying Howie. You're going to, well, actually, your winnings would be zero because Howie doesn't make you pay him. Howie has enough money. Use the range rule of thumb to find the usual outcomes. Well, you've got the minimum usual and the maximum usual. The minimum usual is the mean minus 2 standard deviations instead of negative. Just like it didn't make sense to say you would get 8.5 green pods out of 8 peas. That's not possible. It's not possible to lose money or owe money on Deal or No Deal. So the minimum usual value is 0. It wouldn't be unusual at all if you adopted that strategy and walked away with nothing. That's less than 1 standard deviation away from the norm. The maximum usual would be the mean plus 2 standard deviations. That's about 500,000 plus 100, 600 and something. Does somebody have it for me? What? 638, 646. Does anybody second that? Anybody get the same thing? Okay. So it would not be considered unusual to walk away with nothing. It would not be considered unusual to win $638,646. It would be unusual to win the million or even the 750,000. But you need to have linked in your head the words expected value and mean, because that's what expected value is. Based on the preceding results, is it unusual to win 750,000 or a million? Yep, because that's outside the range of usual values. All right, very quickly, we've got to talk about this last example, because if we don't, I'll get a million emails about it. And let's see, you've got one just like it in the homework. The expected value of life insurance. Life insurance is a gamble. The insurance company is betting that you'll live because the insurance company knows the average life expectancy of a person, male or female. Actually, when you buy life insurance, you're betting that you'll die before the next premium is due. And if you do, you want your family, your whatever, to have money. So there's a 0.9968 probability that a randomly selected 50-year-old female lives through the year. If you're 50, there's over a 99% chance that you're going to make it to 51. A Fidelity Life Insurance company charges $226 for ensuring that the female will live through the year, but if she doesn't, the policy pays out $50,000 as a death benefit. From the perspective of a 50-year-old female, what are the values corresponding to the two events of surviving the year and not surviving the year? If she survives, is she going to make money or lose money? She's going to lose money. How much can she lose? her premium. That's the most you can lose, your premium. The insurance company doesn't make you pay them if you live. So if she survives, then she loses her premium. What if she dies? Well, she doesn't really gain anything, but her estate gains something. How much? Not quite $50,000 because you have to take out the premium. All right. If she dies, then the estate, you could call it net gain, is the $50,000 minus the premium, which would be $49,774 if I subtracted correctly in my head. That would be the profit to the estate. So if she dies, if she lives, she loses $226. If she dies, the net gain to the estate is $49,774. If the 50-year-old female purchases the policy, what is her expected value? Well, that makes me think that I need a probability distribution. I'm just not sure what to put on it. What are the two possible outcomes? That she lives or dies. And in monetary terms, if she lives, she loses $226. So that's one possible outcome, negative $226. The other possible outcome is $49,774. What's the probability that she will lose her $226? The 0.9968. She's probably going to live. She's probably going to lose her $226. So the probability that she will lose $226 is 0.9968. How do you find the probability that her estate gains almost $50,000? 1 minus that, 0.0032. So how do you get the expected value? What's the same thing as expected value? The mean of the probability distribution. List 1, list 2, and then use one variable stats to find the mean. I'm not going to take time to punch it in because I want to have time to answer this last question, but does somebody have her expected value? Miss Danielle, do you have it? You have negative 226 and positive 49,000 in, let me see the stat editor, make sure you got it. And yeah.
Negative 66.
Yes. And that's what you got, right? Negative $66. The female, let's call it average female, the average 50-year-old female would lose $66. What that is actually saying is if the company sold, let's see, tens, hundreds, thousands, 10,000, if the company sold 10,000 of these policies, 9,968 would lose their premium, and 32 would get the $50,000 payout minus, the premium amount. So the insurance company is making $66 off of everybody who bought the policy. If they sold 1,000 policies, then their profit would be $66,000. So the answer to this last question, can the company expect to make a profit from such policies? Yes. Each policy holder would yield an average, and that's in quotation marks because it's really mean, an average of $66 profit for the company. So they sell 10,000 policies. Yes, they're going to have to pay out on 32 of them, but on 9,968 of them, they're going to get to keep most of the premium. All right, you have one just like that in the homework. Look at the P hybridization example and the deal or no deal example and the insurance example before you email me. But if you need to, email me and I'll answer.